start. And I think we should mention the storm
Go 16.
chasing.
Go 16. We have to show that.
Yeah. And the storm chasing and the March 11th.
I will prompt you for the date of
Okay.
the spotter training.
So we are streaming.
Okay.
Make it live.
Okay, great. Sure.
Even though I know my phone.
How do you say make a point that it's majorly discounted?
Well, yeah, we're starting at like 10
Or I would just say if you
5.
make a donation,
Make a donation.
make a small donation, so $5, $10. At this point, it's great, right? We need to get rid of it.
Okay. I got it. Yeah, that would be great. Are you going to be here tomorrow? Okay, then I'll get to you tomorrow. Hey, how's it going? Yeah, it's good to see you. Welcome. You haven't been to this part.
Okay. Yeah, you fly out here in the Pacific. See Hawaii out there. You can see the big island, Maui. Good, you? Ditto. Some, oh yeah, some faculty do. They have a little clicker and all the students have to buy one before the semester. Oh really? Yeah. Or rent one. Oh, with apps? Yeah. I think there's some instructors now using apps to be able to do that.
Just go to our website here. Load up a website in the browser. ABS. See all the
Thank you for being so darn patient.
Thank you.
That should be about right.
Plus interest. Thank you very much. That's it. That's good. That's good.
That other mic can't be there, huh?
Good to see you.
The other mic won't operate independently of that one. So very well. Like if people start asking questions, we'll just like repeat the question.
Yeah, I'm ready to not wear it.
Hey, Eric, at the end, if anybody asks a question, just repeat it so the live stream can hear because there's no audio.
has to run away. I sit around and wait way too long and then have to run away. So it's just a completely different philosophy. Actually, last year, that Colorado storm, that was the biggest mistake I have made. And
The ray.
I waited a minute too long to go ahead of like super traffic, and then I turned on the wrong road. I'm speeding at Dan. I'm like, go fast. He's going 45, and I'm speeding fast, like pedal to the ground. He's got to be. It was hilarious. Although, would have in hindsight, would have been better to stay and let it cross. That's where Skip got. Hey, do we know, Paul? Do we know who our speaker's going to be? Are we going to maybe do one that week? I just found out today that Scott's going to do it. But if he's coming in Friday, do you want to do a special Friday night? But I'm thinking maybe we'll do a virtual. I could. Who did that?
All right. Maybe. Test. Okay, we're good. 6 o'clock, let's get started. Happy New Year, and welcome to the first meeting of Chicago American Meteorological Society 2017. So I know it took us a while to get something organized, but we've been busy with the start of the semester and trying to get that's the delay in the lives. It's the delay in the live stream, so we may have to turn that part down, so otherwise Eric is going to be really confused talking. Okay. Close this guy. Okay, yeah, that would be really confusing for Eric. A couple of housekeeping items. We have very quickly first an announcement from our student chapter, and our president is Amanda. So Amanda, wave your hand, and she wants to give you a quick announcement about our student chapter. I won't say anymore. Go ahead. Yep. So they're on the they're extra sale, for sale. Yeah. You only have to pay for 11 months. Other housekeeping item, we have a couple of events. The first event that I can think of off the top of my head would be Advanced Spotter Training at Wheaton College coming up on March 11th. And right now we have an invitation into James Spann from Huntsville, Birmingham, Alabama area. He's an on-camera meteorologist there, pretty widely known after the April 27, 2011 tornadoes across the southeast. So that's an event we have coming up. I wanted to also mention our thunderstorm lab program here at College of DuPage. 3 of our 5 trips, I think, are already close to being filled. So if you're interested in our thunderstorm lab program, either see Paul or I, and we can get you some more information about how and when those trips are and that sort of thing. So just let us know. Some other really cool stuff. Obviously, last fall we had a GOES 16 talk from Dan Lindsay, which was GOES R, now GOES 16, and we haven't really had a talk or showing you any of that imagery. This is the very high resolution global first disk image, true color, that came from GOES 16 on January 15th. And here I'm zoomed in over Cuba, and you can see Jamaica fairly well here. And just some of the incredible pictures that GOES 16 is going to be able to provide to us. And Eric, probably our speaker tonight, knows no better how this will be able to change the operational side of forecasting, especially in severe convective storm situations, and a lot of the other assets to this, the lightning mapping array and some of the things that Dan talked about. So keep your eye on our website. As soon as this comes available to the public, we're going to try to get this imagery on our website as soon as possible, even though I think our servers are probably going to collapse if we try to process too much of this data. So I wanted to show you that. You can go to the nesdis.noaa.gov website and go to their GOES 16 image gallery to check out some of the first pictures that were coming back. And many of you probably saw the infamous picture with the moon that first came out from GOES 16 a few weeks ago. So be on the lookout for that. That will be a new tool in our tool belt here come the next 30 days or so, I'm told. Any other housekeeping items, Paul, or any chapter members have any sort of things that they'd like to bring to our attention before I introduce our speaker for tonight? Yep. Yep. Many of you. Okay. And many of you who have been here before know Patty, who's our other executive board member, our treasurer, and we're doing fine with budget. So we don't really have to worry about if you have even suggestions of people that would have to travel here, we could give them some sort of offset of travel stipend. So just contact me either through Facebook or email and let me know. So it's nice to see a lot of the older chapter members, the chapter members who have been around a while, come back and visit. We'd love to see you, as long as a lot of new faces too from our classes this semester. So welcome everyone. This is our first meeting of the semester, like I said, and our featured speaker is from not too far away, the Chicago National Weather Service office, you can see, and some colleagues. His name is Eric Lenning. He's the Science and Operations Officer at the Chicago National Weather Service office there in Romeoville. And I was brainstorming with Eric and some titles, and he said, we're doing this really cool winter weather test bed at the Chicago office, focusing really on precipitation type. Now, this winter, we really haven't had a lot of these situations to deal with, right? But these can be quite challenging, and especially with the urban corridor of Chicago, the very low-level boundary layer where a lot of cases, you might have a freezing rain profile, but the urban heat island effect makes that sort of not be the case. And this precipitation falls into the warm dome, and you end up with rain at the surface rather than something like freezing rain. And that's becoming, I think, more common across the Chicagoland region in recent years. But I'm looking forward to this talk. Eric, BS from Bachelor of Science in Meteorology, University of Missouri, and then he got his master's from Florida State, and then a computer science degree back in Missouri, wasn't it? Something like that. Got a computer science. So, Eric, I told you students computer science was important, but I'm sure Eric will show some diagrams and pictures and that sort of thing. So let's give Eric, who's a chapter member, our first chapter member speaker in our Secret series, let's give him a warm welcome. And he's going to talk to us about winter weather precip forecasting. So, welcome, Eric. I've also asked Eric, and I'm going to do this for all of our speakers that we have, to get a little overview of how Eric sort of got to where he is. See how the chemicals may hop around, or essentially not hop around in their jobs in their career cycle. So let's give you a perspective of what Eric went through.
Are we okay on the microphone? Is that streaming to the web, I guess, hopefully, correctly? Okay, so anyway, I'll speak up, so hopefully you can hear me in this room, but I appreciate the welcome, Victor, and I'm really happy to be here tonight. I think this is a absolutely wonderful organization that the Chicago area has, and it's really great to be part of this as a meteorologist or as a student taking a class related to meteorology. I think it's great to be able to bring those groups together and talk about some science a little bit. Victor had asked me to give you a little bit of information about my background. He mentioned undergraduate degrees in meteorology, a master's in meteorology. I got another master's in computer science, and I'll explain why in a minute. But I started my career after grad school at a company, it's called Litton PRC, and they were putting together the AWIPS system for the National Weather Service. This is like 97 time frame, and their work for me involved the testing of the software and hardware, the documentation of how everything worked, and then the visiting of weather service offices to teach the meteorologists how to use the system. And I did that for about a year and a half, left and got a job in the National Weather Service. My first job was at the Techniques Development Laboratory, which was responsible for developing model output statistics. I don't know if you ever look at MOS guidance for your forecast assistance, but I developed that for about a year and then got a forecaster job in the St. Louis office. and only did that for about a year and a half before I became the IT officer, responsible for taking care of the AWIP system, which at the time was still pretty new to them, so they needed someone who really understood it inside and out. So at that point, I think my IT skills had gotten me 3 jobs, and I didn't actually have a degree in any kind of information technology, so I went back and got a second master's degree in computer science. So I felt like I had a little bit stronger foundation in the system administration, in the database, in the programming, and because you can pick it up a little bit on the side, and I got quite a long way doing it in that fashion. So I got this master's degree in computer science, and I jumped back to the meteorology side shortly afterwards, and the science and operations officer here in the Chicago office. I'm responsible for overseeing forecast operations, forecaster training, managing the student volunteer program if anyone's interested, and local research, things like that. So anyway, that's a little bit about my background. If you have any other questions, we can talk about that later on. So as Victor mentioned, we are in the midst of a little test bed at our office to see if we can improve our forecasting ability for mixed precipitation. And I'm going to explain to you what we're doing that's a little bit different than what we have done in the past, and so far we think has been much more effective than what we've done in the past. And this is certainly not a project I'm working on alone. Some of the other key players are listed there. All 3 of those are forecasters at the office. But we've had a lot of help from everybody on staff. So just a quick overview of what we're going to be talking about. We're going to look at the Weather Service forecast process in case you're not familiar with how we actually go about creating our forecast. And then we're going to look at this particular forecast challenge is mixed precipitation. So it looks, just 2 topics. We should be out of here in, 10 minutes probably? So what I'm talking about with mixed precipitation is in the wintertime, rain, freezing rain, sleet, and snow. And sometimes you can have all 4 of those together. Sometimes you can have all 4 of those at the same time in different locations around the area. So it becomes quite a challenge to stay on top of. And in order to understand a little bit about why it's such a challenge, I wanted to take you through what we do at our office. And we kind of stumbled on this. This is not something that we said this is what we're going to do. We looked at everything we do and decided this is what we do. And the one that you might be most familiar with is in the right-hand side where I say forecast. So we do actually forecast. It's called the Weather Forecast Office. And we also rely on the forecasts produced elsewhere. So the Storm Prediction Center produces thunderstorm outlooks. The Weather Prediction Center, they provide guidance as well. So there's forecast guidance from lots of different sources. And so some of the forecast information we generate locally, and some of it we utilize from other sources. But it's all National Weather Service forecast in our eyes. We also then have to deliver that forecast information in the form of products, our zone forecast product, other products that we send out, severe thunderstorm warnings, whatever type of product that we issue the information. Services would be like web services or other types of ways of delivering that. Sometimes we'll send an email to certain partners. And then DSS is decision support services. We may have face-to-face interaction with some partners. We may give a conference call ahead of severe weather or ahead of winter weather. We have a hotline to the city of Chicago. We'll talk to them. So all of those are ways of delivering the forecast information. It's no good just to produce the forecast and then sit on it. But that's really only 40% of what we do. There's 3 other circles over there that I put in the category of program work. I think the shift work consists of the forecasting and the delivering of that forecast, but you don't stop at that. You also have to assess how good were the forecasts, how well did they verify, where was the science lacking, what could we have done differently next time, or how well did we deliver that information? Is our website as useful as it could be? Was that PowerPoint that we sent out, the slideshow, did it convey the information? Did our social media services mislead people or were they updated frequently enough? So we were always assessing the value of the forecast as well as how it was received. And then if we see a shortcoming either in the science or the service, we develop new tools, new techniques, new products, new services. And then we have to train. We have to train us and our forecasters how to use those, and we have to train our users. We do a lot of that. We work with the FAA, we work with ship captains, we work with City of Chicago, we work with emergency managers so they understand how to use our products. And we also get feedback from them about what's working, what's not working. And then we start the cycle over again. So that's a lot of work beyond what you may think that we spend most of our time doing. Tonight we're just going to talk about one little aspect of that, and that's forecasting. And even among that, we're just going to talk about one little aspect of the forecast, and that's the precipitation type. So in the old days, what we would do is we would actually manually write out the forecast. When I first got in the Weather Service around 2000, we would sit down and type the forecast. We might group several counties together and give all those counties the same forecast. We'd break it out into 12-hour periods like today, tonight, tomorrow. And we would give the basic elements, the temperatures, the sky cover, what the winds are going to be, and whatever precipitation chances and types of precipitation. So it was a really straightforward thing to do. And you sat down roughly twice a day and wrote this out for each group of counties. It's changed a little bit since then. Since about 2002, we have been producing digital forecasts, and those are what we refer to as the grids. And if you've ever been to our office and seen our graphical forecast editor, you'll know what I'm talking about. I have an example that I'll show in a minute, but instead of grouping several counties together and giving all of them the same forecast, we now have actually thousands of 2.5 kilometer squares that we're producing the forecast for. And we will do that at hourly resolution, or 3 hour, 6 hour, 12, but a lot of our forecast elements are hourly resolution at 6,000 plus grid squares. And we have far more elements beyond just the basic ones I listed above. And in addition to those elements, some of them have components that need to be computed and derived before you can actually create that element. So you'll see what I mean here in a minute. Temperature, dew point, relative humidity, apparent temperature, maximum and minimum temperature, the probability of precipitation, which we call the POP, the QPF, or quantitative precipitation amount, the snow amount, the ice amounts, significant wave height for Lake Michigan, sky cover, that's the partly cloudy, mostly cloudy, wind direction, wind speed, wind gust. Weather can have lots of different types of weather. You can have the precipitation related and the non-precipitation. So fog is weather, freezing spray is weather, water spouts is weather, but none of those are precipitation elements like snow or freezing rain or sleet. And then we have different hazards. So we may have dense fog advisories, heat advisories, winter weather advisories, freezing rain advisories. It goes on and on. So we have lots of different weather hazards that we have to be responsible for. And in addition to all those, which are the basic elements you're probably familiar with, we also produce fire weather grids, so Haynes index and mixing heights and other stuff I can't remember right now. But we have graphical hazardous weather outlooks. So we'll have grids showing the area where gales are likely, or where dangerously cold temperatures are likely. Dangerous heat in the summer, we also convey that graphically. We have marine grids that I mentioned the wave heights already, but we also have different wind grids because the ships are at different levels out there on the lake. And we have aviation grids we're experimenting with for ceiling heights and visibility and things like that. Again, all these are 2.5 kilometer squares and often hourly resolution. And then the POT, probability of type. So that would be for the weather. Probability of the weather type being sleet or snow or freezing rain or drizzle or freezing drizzle or so on and so forth. So that's a little bit beyond typing it out, but we still just do it with 2 people. So this is what the graphical forecast editor looks like. And our domain consists of nearly all of Lake Michigan and then the counties that you can see there in white. So 23 counties across northern Illinois, northwest Indiana. And the forecast elements are shown there on the left. Temperature is at the top. Dew point is below that. relative humidity, max temperature, apparent temperature, which is either the heat index or the wind chill. Wind gust, 20-foot wind, sky, weather, and there's many more. So, in fact, it scrolls off the page, and this is only a subset of all the elements. To edit this information, there's a menu I just circled at the top. It says populate. There's lots of tools you can use to populate. They're called smart tools. They're not always smart. The E is another just way of accessing the editor tools. We have a little bullseye, which means we can draw contours if we want to contour precip probabilities or temperatures. There's a pencil. We can just draw and get the numbers we want. There's a thing there. We can circle a part of the grid and assign a value or apply a tool just to a certain area. We'll use that a lot for the lake because things behave differently on the lake. So we have all kinds of tools. But this year we have a new tool, and it's called Forecast Builder. And it's actually a composite of lots of different tools. And it's actually, I think when forecasters first heard about it, they were kind of worried that it was just going to, like take their jobs or something. We're always worried about the next thing that's going to take our jobs. We're really kind of terrified about that. It hasn't happened yet. And Forecast Builder is actually a way just to help us do our jobs a lot better and a lot more easily. It helps you maintain consistent grids so that you're not producing snow when it's 50 degrees, or you're not producing freezing rain when it's 50 degrees, or you're not producing rain when it's 24 degrees in your grid. So it helps you be consistent that way. It makes it easier to maintain. It actually walks you in a methodical way through the forecast process. And most importantly, in my opinion, it provides a common set of tools that all the forecasters are going to use. And that way, if there's a strength or a weakness in the tool, everyone has advantage of that strength, and it's more likely that you'll see the weakness and be able to correct that weakness, and then everyone will benefit. So we've been testing this tool this winter across a large portion of the central region in the Weather Service. But locally in Chicago, we have a separate test bed that's really specifically tied to the precipitation type. And so when you're going through this process, you start at your foundation, your base grids like temperature, probability of precipitation, relative humidity, things like that, wind. And then you step to these next two, which it says top-down grids and precip types and accumulation. So top-down refers to not just what's happening at the surface, but what's happening above the surface, which is really important for precipitation type. And then once that information is entered by the forecaster or edited, then you can derive your precipitation types as well as the amounts. You don't want to have snowfall accumulation if you aren't forecasting snow, for example. So it will help you keep all of that together. And we'll look at this process in quite a bit of detail as we deal with the forecast challenge of mixed precipitation. So I don't know if anyone has had access to this top-down methodology, if that's been introduced in any classes. It's not something that is easy to wrap your mind around the first time you hear it, so I will I'll try to take it slow enough that if you're unfamiliar, it makes some sense. And if you are really familiar, you'll find it very interesting too, right? So we have a forecast temperature profile in the atmosphere that starts at the surface and goes up to 500 millibars or more. And within that layer, you might have warm air above freezing, or you may have a lot of cold air below freezing. You may have parts of it that are saturated and parts of it that are not saturated. In this particular sounding, the red line is the temperature, the green line is the dew point, so they're very close together. They're mostly saturated all the way up. The thicker blue line shows the zero, the freezing line as it goes up in the atmosphere. So you can see in this image, there's a warm layer, 750, 800 millibars, where the temperatures aloft are above zero. And if a forecaster is looking at this sounding, they're asking a lot of questions about the information they're seeing. They're asking at the top, how cold is it at the top of the sounding? And is it saturated enough for you to have ice in that sounding? Because if it's not saturated at a cold enough temperature, you won't ever actually produce snow or ice. You'll just get a rain or freezing drizzle type situation. You look, for example, also whether there are any dry layers below that, because the snow could fall and it could evaporate aloft and never actually make it to the surface. And if it's a shallow enough dry layer, you could actually get a cedar feeder type situation where the snow aloft is falling into a saturated layer below that on its own might not produce any kind of precipitation, but once you start seeding it with snow, it produces very effective precipitation. And then if there's a warm layer, you want to ask, well, how warm is it and how deep is that warm layer, because that will affect how much melting you have of the snow. Below that, you have perhaps a cold layer near the surface. And if you've had melting aloft and not enough cold air, you're not going to refreeze. You're just going to get liquid to the surface in the form of freezing rain or freezing drizzle. But if there is a lot of cold air, or if you haven't melted much aloft, you are going to end up with a situation where sleet is more likely, because you've melted and then you're refreezing. So it's a fairly complicated process. The problem is we don't, again, do this for points. We do this for several thousand grid squares. And we do this every hour and out to 7 days in some cases, or at least hourly through the first 2 or 3 days, or 3 or 4 days. And we have to make this jive with all the other weather elements at all these little squares. So that's our forecast challenge. So back in the old days, you know any of these guys, Paul? Are you any of these guys, Paul? So, in the old days, we might just say, well, if it's below freezing, we'll call it snow, and if it's above freezing, we'll call it rain. If it's right at 32, we'll just call it a mix. And then we do some more research, and we evaluate, and we say, you know what? I have seen situations where you can get snow above 32. So you refine your technique, and then you start calling the 32 to 36 a mix. And that's science right there. You could also have a little more sophisticated approach. The models that run at INCEP, they have two ways of producing precipitation type, either implicit by taking the model output, temperature, humidity, and so forth, and running some post-processing routines. Those are some of the ones listed there. But you could also do explicit technique where you actually look at the model microphysics and what it's producing in terms of the precipitation type. The explicit are far more computationally intensive, and so the implicit are greatly preferred. But occasionally, this is, I know, surprising, but the models aren't right, and we have to do some local manipulation, or maybe we want to blend the output from a couple of models. So we locally have to have the ability to come up with a precipitation type. This will be kind of a little group quiz here, but very informal, where forecasters see profiles like this, they kind of know what to put into the forecast, roughly speaking, in terms of precipitation type. And to make it a little bit easier, I'll draw these red lines. That's the freezing line. So at the first image there on the left, it's mostly below freezing except for a little nose of warm air aloft. And does anyone want to volunteer what kind of precipitation they would forecast when you just have a little bit of warm air aloft and everything else is below freezing? We have a sleet. We have a vote for sleet. Grapple. Snow grains. Aren't those all the same thing? No. Anyone else want to volunteer? Victor thinks there could be some snow in there. Paul says wet snow. So we have a difference of opinion. I think, personally, that looks like a pretty good sleet sounding, but how about the next one? A lot more warm air and less cold air below that. Okay, freezing rain. The third one we have, it looks a lot like the first one, but what's different about it? Yeah, it's dry air above that warm layer. Somebody said no ice. It's not going to be saturated cold enough for you to have snow, so you're going to get like a freezing drizzle because you're warm aloft and then cold at the surface. Even if the entire thing was below freezing, but not cold enough, you could still have freezing drizzle. And then the fourth one, the entire one is below freezing. So I'm hearing snow. Okay. So yeah, you can do this, and you can do this, manually. But for every single, those 6,000 grid points for every hour, you can actually also write a tool to do this, and so that's what we're going to be looking at. The tool, we have this idea that the forecasters should be able to use their discretion or use their favorite technique maybe, or if you want to write a tool, maybe you're a fan of the Hillworth method, and that uses 850 wet bulb temperature and 1,000 millibar wet bulb temperature in this little nomogram. I'm personally not familiar with the Hillworth method, but somebody could write a tool to use the Hillworth method. You could write a tool to use partial thicknesses, and this uses the 850 to 700 temperature layer thickness value and the 1,850 thickness. And then the thicker the layer, the warmer it is, and the thinner the layer. So if both are very deep layers and it's very warm, if it's deep layer aloft but it's shallow at the surface, then you have warm aloft and cold. So you can come up with sleet or freezing rain, rain, snow, using partial thicknesses. Or maybe you want to use this nomogram for partial thickness, or maybe this nomogram for partial thickness, or maybe this nomogram, which you might recognize from Buff Kit if you've ever used that one. But all of them use the same, 850 to 700, so they're all using partial thicknesses. Wintry mix. Yep. So we think maybe we can do it maybe a little better. This is the top-down approach that has been popularized in the Weather Service for probably the last, decade, almost maybe 20 years now. And a lot of good research went into this. And one of the key components is the max temperature aloft. And you can either use temperature or the wet bulb, but the max temperature aloft, when you're only less than 1 degree Celsius aloft, you're not going to get much melting. So let's just call it snow is the way that this works. But as you get into the 1 to 3 degrees aloft, then you get more melting. So you have a better chance of melting, but maybe not completely melting, so that you can refreeze that little pellet of sleet. But then you get above 3 and you're so warm and you've melted it completely that when it falls to the cold layer below, you're not going to be able to refreeze it because it's completely melted. There's no ice in it anymore, and you're going to end up with freezing rain. So that's the max temperature aloft is a real key component of this, and some of you may have had training in this technique, and it works pretty well. I think they say roughly 80% of the time this works pretty good, but some of us might say, well, there's another 20% that matters. But looking at it in a little more detail, it's kind of a graphical version of what I just showed you, but as you're below about 1.5, the most likely type is snow. As you get closer to the 1 degree mark, your sleet chances increase. Your sleet becomes dominant when you're about 1.5 up to about 3.5. And then above that, then your liquid becomes dominant. And that liquid could be freezing rain or rain, depending on what's happening at the surface. So that's just kind of a graphical version of that. So a little quiz here. What precip type would you expect given this profile? Based on what I just showed you, assume it's saturated. The max temperature aloft is about 1 degree, and the surface is about 34. So sleet, snow, Victor says. Come on, I just trained you. Anyone? They're saying sleet, snow. Anyone else have other thoughts? Does anyone agree with them? Based on what I just showed you, Paul agrees. Okay. So, yeah, that would fall right there. So the snow and sleet mix based on that max temperature aloft. And maybe a small chance of rain there at the bottom. And other people have looked at this and tried to say, well, maybe it's not that great of a graph. Maybe there's a better chance of sleet and a better mix of liquid and snow. So you can play with this. You can do research, and you can, just like those old guys around the desk, you can say, well, I've observed that it's, maybe not always behaving that way. What we've done locally, though, is we've started to use this technique. It is based on well, I'll say it, Burgoyne. That's not how you pronounce the man's name. It's more like Bourgois, but I'm not French, so we're gonna go with Burgoyne. I did take a class with Canadian meteorologists, and they got angry. So hopefully we're all cool. We have a way of computing the actual amount of energy in the sounding that's above or below freezing, just like you would compute CAPE, and you do it in joules. So in this case, you have melting energy of 35 joules, 35.5 joules, and then a little bit more in the surface layer. And so based on research by Burgoyne, you actually would get total melting and not enough energy to refreeze. So this would actually be a rain sounding. And at midway during this event, it actually was completely rain. And so the question is, what about refreezing the sleet? You have a negative energy of 49 or negative 49 joules. And I'll show on a chart later on why that would not be sufficient to refreeze. But here's a little bit closer look at it. Positive and negative areas is how it works. And if you have a little bit of positive energy aloft and a lot of negative energy at the surface, which is being depicted in that upper left, that's a good sleet type sounding. As you get more warm air aloft and less cold air below it, you're at the freezing rain area. And if you're just dealing with a single warm layer at the surface, do you have enough warm air to actually melt that snow? Once you get above about 13 joules, snow becomes pretty unlikely. And once you get above 5 joules, rain becomes pretty likely. So in the middle there is a mix. And we know that there's a mix often where you have rain and snow. So it matches kind of our understanding of how things work. So the other thing that I like about it very much is that you don't need to know your freezing level, you don't need to know your max temperature in the layer, you don't need to know your surface temperature, you just really need to know the melting area. So here's an example of you have a warm layer at the surface, and I did math for that triangle, 0.36, but that triangle also has an area of 0.36, much higher freezing level, much colder max temperature, much deeper layer, almost isothermal. And that triangle has the same max temperature, but way less melting energy. So I think it accounts for what's happening a little bit better than just blindly looking at one variable. And you can adjust that for elevation, which is nice too. Not here, but out west. You can calculate it with temperature or wet bulb. So in this case, here's your 0 and your +5, and here's your other isotherms, and there's your temperature and wet bulb, and various surface temperatures. But there's your calculation, probability of snow, that's POS, probability of snow, and then that's based on the wet bulb. So those values are available in BuffKit if you look in that software. So BuffKit also shows you the melting energy for snow. It lists freezing level. It's not actually used for anything, so I'm not sure why it's on there. But snow, it's 100% that you have snow up to about 13 joules, and then it becomes 0% as you get over 20 joules, according to his technique. With liquid, you would start introducing liquid around 5 joules, and then over 10 joules, it's a 100% chance that you have liquid. So again, there's that area where you have a mix of the rain and snow. We have done some local research and found that maybe his original slopes were too steep. So he was saying that as you get a lot of warm air aloft, you need a ton of cold air at the surface. And we found that you really don't. You don't need as much as he thought that perhaps you did. So we redid this, and these are the new probabilities that we're using. And that little spot right there is the midway sounding I showed earlier. And it had about 35 joules of positive energy, which is the bottom axis, and then about 50 joules of the negative energy, which is 49, I think. And that was not enough to take it out of the sleet, or take it into the sleet area. That was a area where the sleet probabilities would be set to 0. So That's that sounding energy plotted here on this chart. And then the same would be for liquid. As you get a lot of positive energy aloft and not much cold air below that, then your liquid probabilities are set to 100, and then you get freezing rain. So again, we'll take a look at this one. And in the original type, we had snow and sleet, but in the new type, we have rain dominant without any sleet or snow mentioned at all, because we're above that 20 joule cutoff. And indeed, that's what happened. So we had a recent success with this. We've actually had several. This winter has not been good for those who love lots of snow, but it's been pretty good for us as we test out these precip type algorithms, because we've had a lot of events of mixed precip. We haven't had too many slam dunk snow events, but we've had a lot where you have rain transitioning to freezing rain, or snow transitioning to rain, or sleet and snow mixed together, or sleet and thunderstorms, as we've experienced several times. And again, we're not just doing this for one point, we're doing this for the entire forecast area. And the tool that we have available to us allows us to do that in a manageable way. And on the left-hand side, what I'm showing is the contoured areas are the positive energy aloft. And the color graphic is the negative energy below that. So what you see is that you have some positive energy overlapping the negative energy. And as you get toward the lower values of the positive energy, those happen to be deeper into the cold air. So you're getting small values of positive energy above increasingly large values of negative energy, which is ideal for sleet. And that is the area on the right-hand side. I was working a midnight shift, and so I calculated the grid, and I put a big swath of sleet across the area. And that area marched through right around daybreak that Thursday morning, and it nailed it. I came outside. Well, this was the sounding. You can't read that, but there's a little positive area of 33 joules and a negative area of about 190, which is great for sleet. This was calculated from one of the AMDAR aircraft soundings out of Midway. But you can see the observation: light freezing rain and sleet, or pellets, in that 12:53 observation. And that was my car there in the parking lot. It's covered with sleet. And it's okay if you forecasted it. It's not okay if you come out and you didn't forecast it. Yeah, well, we put those up. So, yeah, and forecasters, they complain a little bit about having to be stuck using the same tool as everyone else is using. But I've already kind of covered the advantages of all being on the same page, because you come in and you know what the person in front of you did, and you know the strengths and weaknesses of that tool. And if you have an idea for improving it, there's a lot of opportunity. And your work will benefit not just you and not just your office, but the entire weather service, potentially. And that's, again, just one element. We have water spout tools and freezing spray tools, and this tool is going to be continually refined. There's really a lot of opportunity right now by all working together to make a big difference. So you're not going to end up with something that's perfect, that matches precisely what the weather is. I mean, it's probably impossible to get it precisely correct. There were events where we had some sleet or snow pellets that we didn't forecast. And, that was fortunately a pretty minimal type thing when it occurred, because this is trying to get at the main impact precip types. You're going to have maybe sleet mixed in for an hour of pretty low impact. You might have a brief period of freezing rain or freezing drizzle. That's pretty low impact. But this is going to get you close. So I asked this question. We're artists like Van Gogh. We think we're producing our forecast masterpiece, or at least that we should be able to. So I'm going to ask, you guys know what's the Starry Night, right? It's real famous. Can anyone kind of describe that to me? I mean, just, he does this. Yeah. So, like that? Yeah. Does anyone think this is not Starry Night? Or is this Starry Night? Night something. Nighthawks. You can go downtown and see this one, right? So, if you're expecting Starry Night, don't give them Nighthawks. That's kind of what I tell people. It doesn't have to be, well, that's Starry Night. But I think if you give them, the one on the left instead of the Nighthawks, the users are going to get the idea. It's not going to be perfect representation of what the weather's doing, but you're trying to get as close as possible so they can make the right decisions. And then, add a little local flavor. Tailor it to what you understand about your local forecast area. So I think that's all I have on that topic. Right, yeah, we are using the model grids. We have the ability to manipulate those. If we think that they're not bringing in enough cold air, then we can increase that, or we can blend multiple models together. Right, right. You have a default when you're initially populating the energy grids. You have a default blend of the models, and you have the GFS, the NAM, the RAP in the short term. We just added the Canadian. We're getting a high-res Canadian now, and you are able to blend those different models together, or you're able to on the fly increase the contribution of one more than the other. If you think the NAM is maybe too warm but the others are too cold, you can kind of tweak it, adjust it based on one. And or you can just go right in there and draw it directly. So you have a lot of flexibility, but you do have the models as kind of an underlying place to start from. Well, what we've seen so far is it's the amount of energy rather than the shape. Now, the traditional technique that just uses max temperature, when you go through that training, it says that you have roughly an 80 or 90% correlation between the max temperature in the layer and the energy in the layer. So that basically means it's a triangular type shape a lot of the time. But they know that there is sort of a shortcoming when it's isothermal because of the amount in that layer, not so much the shape of the layer. Yeah, and that's, that's a really good point. He mentioned that the fall speed of the hydrometeor would be a factor that this wouldn't account for. It just, what kind of accounts for it, which is kind of neat because your probabilities increase based on the amount of warm air and cold air. It doesn't automatically turn on and turn off. And so that's nice because your probabilities of sleet decrease as the profile becomes less favorable, but they don't immediately go to zero. And that's sort of an indirect way of accounting for hydrometeor variability. The idea that as you have a little bit of warm air aloft, you're going to have some melting of the smallest hydrometeors, and those are going to fall as sleet potentially. And the bigger ones are still going to be ice. And as you have more melting, you're going to have the bigger ones start to become more liquid, while the small ones are totally liquid. So that varying probability does indirectly count for hydrometeor size. There's a researcher, Heather Reeves, out of, they all work for several places down there. Oklahoma Sims, NSSL. But she's done a lot of research on actually, it's called a spectral bend precipitation type. So she will directly forecast the probability of precipitation type for several different sizes of hydrometeors. And I think, that makes a lot of sense. It may end up getting to the same conclusion that we reach, because you end up with mixed precipitation when you have, those marginal thresholds of warm air and cold air. So she's done a lot of good work that looks at that directly, but this indirectly accounts for hydrometeor size and the melting and the fall speed, which is all going to affect what you end up with below that warm layer. Yeah, well, if you just have one warm layer and that's at the surface, then all you have to look at is a warm layer, which is nice. It simplifies things a lot, and then you can start to say liquid gets introduced around 5 joules and snow goes away around 20 joules, things like that. It's not as straightforward when you do have a warm layer and then the cold layer. You can't just look at the cold energy and say that's enough for sleet or that isn't enough for sleet, because it does depend on the energy aloft. So that is kind of tricky for the forecaster, because they don't really know what to expect until they run the tool. They know when the potential exists because you have the warm energy overlapping the cold energy, but it's a little bit of a mystery until they run it, and then that's not what I wanted. So then they have to figure out why it came up with that result. So that can be challenging. It compares the two areas, but it's not sufficient to say that this amount of cold air alone automatically produces sleet. Now you mentioned like CAPE. You have positive CAPE and you have negative CAPE. Negative CAPE would be for the like the convective inhibition at the below the positive area. I think it's maybe, depending on how much forcing you have, you kind of get to a point where you understand there's just very low chance of getting thunder today because of so much negative energy, especially when there's no boundary around. You also get that situation where you have so much cold air that whatever liquid, whether it's a ton of liquid or not much liquid aloft, you're also going to end up with sleet just because there is a massive amount of cold air. So in that way, it is probably a little bit similar to convection. Yeah. So he had two questions. One, what potential caveats or drawbacks? And then the second would be what name we have assigned to it. I laugh. Kevin Burke has done a lot of this work, a lot of this research. He's the one that revised those milligrams. He calls it the pure energy technique, and he's doing that. So that's our local nickname for it, but we call it the energy technique, which actually calculates the energy versus the max temperature technique. So the second one, the caveats, the drawbacks. One really big challenge, but this is true with the traditional top-down. I think our biggest challenge and the thing that gets us tripped up most, maybe Mike would chime in, but probability of ice that I didn't even mention. But in addition to knowing what the thermal profile is, you have to know if there's actually going to be ice to melt at all. Because if you don't have ice to melt, then this whole thing gets thrown up, and you end up with freezing drizzle or freezing rain. And so your probability of ice, or I think we call it prob ice present or something like that, is still probably the biggest challenge both with this technique and the traditional top-down. Because if you get that wrong, and you say that there's going to be ice introduced when there's not, your forecast is a goner. Or if it comes through and you do get ice that you weren't expecting, your freezing rain forecast suddenly turns to heavy snow, maybe, and that can be a real challenge. So, yeah, and what I'm talking about when I'm talking about ice being present, even in the summer when you have thunderstorms, that rain starts as snow up there in that cloud. Heterogeneous nucleation, you get ice and the growth of ice onto ice nuclei. And you need to be cold enough for that to happen. If you're only -5 or -10, you're not going to have a real great chance, I'm talking -5 or 10 Celsius, you're not going to have a real great chance of having ice or heterogeneous nucleation in that cloud. And that's true in the wintertime as well. If your entire sounding is only saturated at a temperature of -5, you're not going to be able to get snow in there at all. And so the probability of ice being present would be very low until it turns into freezing rain, at the surface. So that's kind of what I mean by that. That when I say ice, that means there's no snowflakes in that cloud. But yeah, even in the summer, that's how most of the rain events start. The NPing is really cool. That's such a clever idea. I have it. Yeah, I have that in my bookmarks for my winter weather, so it's loaded all the time. Thanks, everyone.
So really, if you're not familiar with this, there's lots of things, there's a little bit of a learning curve to using this stuff, but you're just zooming out. You can do it at the national level or local level. And each of the little icons, this is probably over some time period, animating, showing you the recent reports of precipitation type, geocoded by GPS on a person's smartphone. So I think the little brown dots are just people that are doing testing, and then there's some sort of legend around here somewhere there used to be. The stars are obviously snow, then we have rain, you can report freezing rain, ice pellets, you can report the whole gamut. The whole idea was to try to improve some of these algorithms now that everybody has reporting based on the phone in their hand, and to really improve radar algorithms. Now we can tell that and I would imagine as a forecaster, verifying your stuff on the fly.
Yeah, and that's great because you can't always tell just from the radar by any means. You can just do a poll what kind of precipitation type you're actually getting near the surface. So having that ground truth is really valuable, and it's fascinating to watch too, especially in mixed events. You could have sleet, snow, rain, all in the same little area, and those are all valid.